Today I'm going to talk about how the other sciences are not based in physics. Welcome to Missing the Mark, where we look for meaning in strange places. I'm Christopher. So obviously I need to clarify what I mean. So when I say based in physics, there's a thing you'll hear that like all the other sciences are just applied physics. The chemistry, you're just looking at molecules, and molecules are made of atoms, which are made of protons, neutrons, and electrons. And, physics says how they work. So if you just work it out with physics and you get chemistry. And, biology is just, sort of applied chemistry where, animals and plants and so on, they're made of molecules. So you're just looking at how these things interact. And since that's applied physics, biology is just applied physics too. And there's some theoretical sense, if you distinguish the map from the territory of, physics, if by physics you mean the territory, not the map, that, like nature is built on nature. And so, there is a sense in which all of these, natural things are built upon the nature of nature. So that's certainly true. And that's kind of just trivial. I mean, that's not telling anybody anything they didn't already know. That's not saying anything interesting about the world, that like natural things are made up of natural stuff. And so, whatever. But the interesting thing here is that this is not actually true in practice. The other sciences have their own methods and their own methods of discovery and don't really use physics, not in practice, not in any sort of meaningful practical sense. There are minor exceptions that you will find and so on. But I first encountered this actually like decades ago. I was talking with somebody she was a I think she was a PhD candidate, but she's a grad student in chemistry. And I asked her, like, how much do you guys use quantum mechanics? And her answer was basically not at all, because the calculations are far too hard to do. So the thing is, like, the number of calculations you have to do really go up with like 2 to the number of electrons in a system. For doing the quantum mechanical calculations for like taking current state and, making predictions on, based on this. And, like to take a glucose molecule, for example, C6H12O6. The glucose molecule, if you work it out, so, carbon has an atomic, things have as many electrons as they have protons, when they're non-ionic. And, so, you work it out, and you've got 96 electrons in a glucose molecule, 6 for each carbon, 1 for each hydrogen, and 8 for each oxygen. That's 96 electrons in a glucose molecule. And if you look up what 2 to the 96th is, and you look up that, like, the current computers are, I forget what's after peta. They do about 1,000. The current best supercomputers in the world do about, like, 1,000 petabytes. Petaflops, floating point operations per second. Now, you'd have to do more than one floating point operation for the actual calculations involved in the equations. But if we ignore that for a moment, and it's not helpful to actually doing them, it would take, I worked out the calculations just out of curiosity, and it would take roughly 300 some odd years to do the calculations for just that the electrons in that glucose molecule. And we're ignoring that if you want to actually do anything with it, it's going to be surrounded by water. So you're going to have a whole bunch of other water molecules, and things, the complexity of this goes up phenomenally. And glucose surrounded by water is one of the simplest things you're going to run into in biology. It's, there are plenty of relatively simple things in chemistry, kind of, sort of. But it's also like super complex. And the stuff you're actually interested in is way too complex to actually run the calculation. So, what do they do in practice? They come up with various models inspired by quantum mechanics that, like, and then you see whether or not they work. And, if they work well enough for your purposes, then great. And if not, well, they don't. You throw them out and you move on. But what you're not doing is actually taking the physics and applying it. You're kind of like being inspired by the physics. Some of the time, you're being inspired by the physics to try, come up with your own models. And so interestingly, just sort of as a side note to that, there's a kind of discussion too about like what is the physics. Very, very frequently, physicists will tell you that physics is nothing but the equations, that everything else that you say about physics is really like it's not the physics itself. It's just the stories you tell around the physics, that is to say the equations, because the only things that are tested in, when you get outside of theoretical physics and you go into experimental physics, the only thing they test are the equations. They don't test the interpretations of the equations. They don't test the theories about what are the things that have the behavior that make the equations. They only test the equations. So the only part of physics that has any kind of verification whatever is actually the equations within physics. And so when you look at it, like those equations, I know there are certain things, like if you throw a cow from a trebuchet, you can use Newtonian mechanics, and you'll come up with a pretty good approximation of what the actual answer of like where the cow will land will be. Assuming a number of things, and you're gonna have to measure a bunch of friction and so on. But depending on how closely you measure, you'll come up with a pretty good example. But they don't throw cows from trebuchets very often in biology, and so they don't really like do that kind of thing. They don't really come up with you will see certain people studying like pressure and so on, and like fluid mechanics comes up there. Although again, like even just doing the physics of fluid mechanics, you don't use say quantum mechanics because you can't possibly calculate this stuff too well. Now, I don't want to overstate this because there are sometimes like inspirations that like things about studying quantum mechanics suggest that maybe there'll be physical properties, but the thing is you have to go find out. You can't just do that and say like, oh, there will be this physical property because quantum mechanics says so. And so like if you have these if you positively dope and negatively dope semiconductors and so on, and you do it with this, you will definitely have this effect. It doesn't work like that. Like you can be inspired to do that, you can be inspired to go check, but there's a whole lot of work that gets involved in figuring out which things actually behave the way we want them to and don't have behaviors we don't want. It is not the case that you can avoid the practical aspect of the engineering of trying it and finding out if it actually works. Because there are lots of things that do not work in practice the way they're supposed to work in theory, especially when like the theory is something you can't actually calculate because there are too many atoms, too many electrons, etc., and you can't do all the calculations. So that is... there is, by the way, sort of an interesting philosophical aspect to this too, because it's like a relatively basic point, and it's worth making on its own, that that even if physics is completely figured out in some sense, which we have no reason to believe that it is, but in any event, the standard model is great. Don't misunderstand me, but there's no reason to believe the standard model is utter complete and physics is over at this point. You run into the you just sort of run into the problem that like that's nice and all, but you can't actually do very much of anything with that. So you come. I mean, compared to the number of things that you want to do, I don't mean literally nothing. I'm saying that in a statistical sense. Compared to all the things people want to do, you can't use, particle physics for them. Higher level physics comes up sometimes, although, even if you like talk to, say, speech therapists, you think like, oh, well, it's a pretty straightforward application. You have, elastic things, and you have, pressure, so on, and you have, the way gases flow, and, Bernoulli's effect, and so on. And indeed, you get some explanation, like the vocal folds. You do get, when the air goes through, you get a low pressure thing that causes them to slam together, cutting off the airflow, the pressure goes down, their natural elasticity pulls them apart again, and you get the next puff, and then the cycle repeats. And thus you get a frequency coming out of this from how often they shut off the air, and then you get the pressure wave hitting the next, then the pressure comes back and slams in and so on. And, that's where you get like whatever frequency that your, vocal folds are, producing. But the problem is like, you can't actually model this stuff well because the layers are sort of like continually changing in their elasticity and in their density. And you are, you're actively, too, using the various muscles in your vocal folds to change things like their stiffness and exactly how far apart they are. And as you change their stiffness, you're changing, all sorts of properties about this. But you're not, like, changing their stiffness all entirely because you have multiple muscle fibers that can pull differently. And you do all sorts of incredibly complex things that each person actually does differently, which is why we all have different voices, for one thing. And you can't, and this is sort of another really, really big problem, you can't measure all the stuff that you want to measure because there isn't the room to measure it all, and you can't like stuff a person full of probes to see like, to measure along 10,000 points what is the density and elasticity, etc., of all of these points without getting in the way. So you can't actually collect the data that you need to do these calculations anyhow. And that actually comes up in a very large number of scientific applications where you will have, places where you could in theory apply science, but you cannot in practice. That you'll get all sorts of things where, like, yeah, if I could put in so many probes and so on that I would know all of what's going on and can feed that all into my calculations, I may be able to run the calculations here. But the problem is you can't do that in the thing because you're interfering with it. And, this is actually, you see this too as a fundamental problem I can't remember it. It's the fact that you cannot, there's a minimum amount of uncertainty. Essentially, the uncertainty in the position plus the velocity of a particle has to be greater than a certain amount. And roughly the problem is that you can't measure both the velocity and the position of a particle without changing it in some way. Because you have to interact with the thing in order to measure it, and interacting with it changes it and introduces it. Well, there may or may not be simple uncertainty that you can't do, but in any event, as a practical matter, you cannot measure a system without changing it in some way, and the smaller things are, the less you have an ability to measure stuff without changing it. So you run into this problem at all scales, though, that like the sorts of operations you want to do, you can't actually get all of the data that you need in order to do it. So this affects many levels of how sciences are not based on physics. In the practical sense, that are not just applied physics. You don't just take the base data, run physics calculations, and there you go. You've done your biology or your chemistry or what have you. That's sort of the practical side. That like there's some trivial sense in which, yes, natural phenomena operate naturally. Yeah, whoop-de-doo. But other than that, yeah, that's why these are separate sciences that people, just conduct differently. And if you actually get to know the people doing them and talk to them about how they do them, read up on how they conduct these things and so on, they actually use extremely different methods and extremely different techniques, and you will find approximately nobody outside of doing particle physics who runs particle physics equations. Again, there are certain things in molecular biology and so on that it will inform them, right? Don't misunderstand me. It doesn't have nothing to do with it, but it informs them, and they need to come up with the techniques to solve the problems that they have with the tools that are actually available in the context in which they're doing them. So, which kind of gets me to that idea. The philosophical side of this, that is to say. And you see this idea that like everything is just applied physics as used to support a kind of I almost said corporate hubris, and it's not corporate exactly. It's more of a vicarious hubris. That is, there are people who know these things, and then so like you see people who will give themselves credit for scientific knowledge that other people have. Usually, the way they do it vicariously is through a sort of like a corporate persona, as in like, we human beings understand physics, which means we actually understand everything, and there are no mysteries left. We just have to work out the details. And that's not true in a variety of ways, one of which is that it's literally impossible for us to work things out using particle physics. There's too much, it's too complex, there's too much going on. You simply cannot do it. Humanity will expire before you have any hope of doing it, because the complexity goes up so absurdly high. Because like most of the interesting things in I give the example of glucose, right? That's a tiny, 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 tiny little itty bitty molecule. The actual things in biology that you do are made of proteins, and proteins have many amino acids, and acids are they have more electrons per amino acid than glucose, and you have these long, long, long chains of them, and the thing is, they often work by their shape. So, just to give an example, enzymes, which are proteins that have particular shapes, and will take, two things that can react to each other if they come in contact in just the right way. And basically through the shape of the of the protein, they tend to pull in the two things and stick them right next to each other in just the right way for them to actually react with each other. And as such, they massively, massively lower the activation energy, because now if you hold them in just the right place, now they'll very readily link up without like having to be slammed together really hard. Because the problem is like often like if two molecules can link up this way, they will like push each other apart over here and do all sorts of, weird stuff. And most of the ways they come into contact will tend to like push them apart. And so they have to be like slamming really hard to finally hit each other and do it right. But if you can hold them and move them into position, well, these enzymes are absolutely freaking enormous. And if you look at the reaction that they catalyze, it involves them in their complex shape with their many, many, many amino acids interacting with the two constituent molecules. So to try to measure that, you're looking at, you can easily be looking at, many, many hundreds of electrons involved in just this. And very, very frequently, the water surrounding the thing is actually highly relevant too. You have more than just one water molecule. You can easily have thousands of electrons that would need to be taken into account in order to run the calculations. And exponentials go really, really badly this way in terms of like being able to actually do them. So and this is probably more detail than most people need, and I apologize. But I just want to point out that like the foundation for this is really, really rock solid. So this is... So the idea of taking this and saying like, oh, well, we know everything, which appeals to a certain sort of subset of people who want to feel like they know everything and there's no mystery in the world. But it doesn't work. It doesn't work even in theory. Like you can't have a physics, with what we know within physics at the moment, you can't have any kind of physics that actually lets you work things out. And this is, of course, compounded by a problem which is very frequently not recognized, which is that all of the work that you are doing within physics is all of the experiments you do within experimental physics necessarily take place in labs. And this becomes a really obvious problem, incidentally, when you look at like social science type things. So like if you want to look at human mating behavior, and you get a bunch of subjects into a lab and randomly assign them to each other, anyone who isn't a complete fool will know that, like, well, they know they're in a lab. They know what's going on, and so there are all sorts of behaviors that will not happen here because those sorts of behaviors are inappropriate to being in a laboratory setting. And you will, depending on exactly what you think I mean, you'll come up with various examples of like, oh, you can have studies of this or studies of that. And, there are people, there are all sorts of studies. There are people who have taken sonograms of a male and a female having sex because they're curious, like, what does the penis actually do in the vagina? And that's the closest way you can do it. And it's funny because a lot of, having read up on that particular one, like a lot of couples have trouble with this because you've got a researcher standing there who is putting a sonogram wand on the woman while the two of you are having sex. And a lot of couples can't perform under those circumstances. An awful lot of couples don't particularly want to. No, that's kind of not very relevant to the simple thing that they were studying, which was like what physically actually happens to the penis within copulation. Like how does how do the structures respond to each other? And so the psychology of the matter doesn't matter in the slightest to that. That's, since they're simply asking a simple physiological question. And, whatever people are thinking or choosing or whatever's, strange about the people who have chosen to take part in this study, it doesn't really affect the simple basic mechanics of it. But a lot of these are married couples, by the way. But not all, I suspect. But in any event, so there's some people who would take part in that. But like, if you're trying to study how people actually choose their friends, well, it just doesn't work in a laboratory setting because that's not appropriate to a laboratory setting, and the people in it know it. Now, it is entirely possible that electrons behave, that electrons have behaviors they will exhibit outside of laboratory conditions, but not in laboratory conditions. It is possible that electrons have behaviors that they only really do if they are inside of a thinking, conscious human brain. That, much like, we have behaviors that we do when we're awake, but not when we're asleep. We have behaviors that we do when we're at school, but not, we have behaviors that we do when we're at a pool, but not when we're, walking around on the land. That, context matters. And so it's entirely possible that electrons have behaviors that they don't do in labs, but they do it inside of a conscious human brain that's thinking right now. And there's absolutely no way to find this out using, scientific investigation, because if you were to try to instrument out the electrons in a human brain, you'd interfere with what they're actually doing. Because, they're supposed to be taking part in the thing, and in order to know what they're doing, you have to interact with them in some fashion, and then interaction with them is going to change what they're doing. So, even apart from the theoretical difficulty of how on earth do you plan to be sufficiently invasive to find out what electrons are doing inside of a human brain, but insufficiently invasive to, keep the person alive and conscious and so on. Ideally you'd even leave their skull intact, because it's actually really useful to have your skull intact. Getting bacteria inside your brain is just not a good day. So, but even apart from that, even in theory, you can't do it, because the moment you're actually trying to measure what individual electrons are doing, you're interfering with them, because you have to interfere to take the measurement. So the point, which I think I've demonstrated fairly clearly, is that we necessarily live in ignorance of what the totality of physics is, because there's a very, very big limit to where we can actually investigate this. There are interesting things. There's a lot of cleverness that goes into looking into how electrons behave in various places and so on. But at the same time, there are very, very significant limits to where you can even try to do these experiments and how you can interact with the things and so on. So another interesting one is, there's some massive problems with, for example, finding out if the gravitational constant's really constant across space and time. And there are particular things that if you have just the right conditions, maybe you might be able to find out if it's different or not. That's not the same thing as saying that you can across all circumstances and conditions. It's complicated. I'm not going to get into the details of that to explain fully, but just suffice it to say that, there are some significant limits to the amount you can actually measure about something that's like a million light years away from you. Anyway, the point is, this thing about physics being the basis of everything, and physics is the standard models worked out extremely well, and no one's been able to break the standard model yet. Except for gravity. I always find this funny. The standard model's been so incredibly robust and has withstood every attempt to break it, except for the fact that it literally you can't reconcile it with relativity. And so we just that just gets ignored all the time. That this is one of the hence why there's the interest in string theory, and people want the grand unified theory, because the standard model of quantum physics and general relativity can't be reconciled to each other. The equations don't work, and they're in places where you can't do experiments to see which, if either of them is correct. Too high energy, too strong gravitational fields. This gets back to what I was saying, by the way, about how there are limits to where you can build physics labs, and there are limits to what you can do in physics labs. And so this is kind of a problem that general relativity, and the standard model of quantum mechanics, they don't work together. And but everyone kind of ignores that for some reason. The two theories contradict each other, and we've verified both to impressive degrees, and every attempt to reconcile them has failed, miserably. If you just look into the failure of, say, string theory, and there are quantum gravity theories, which also none of which have worked. Interestingly, this is a complete tangent, and I apologize, but it's interesting that, for the most part, most attempts to reconcile quantum mechanics and relativity gravity in particular, have tended to go in the direction of adding a bunch of extra dimensions to the three we can observe actually exist. The XYZ dimensions. We can observe those three, and we do not observe any others. As the saying goes, don't at me with time as the fourth dimension, because you can't move freely along that dimension. The time is it's not a dimension in the same sense, anyway, and so the point being, they've all tended to add these extra dimensions, and because that solves a bunch of problems, but then you get the massive problem of you then have to hide them again. And I think it was Lee Smolin who pointed this out, that in his book, The Trouble with Physics, he's a physicist who's talking, he's a quantum gravity type guy who's talking about the trouble with string theory. And the basic problem you run into with all attempts to solve your problems using extra dimensions is that you lose whatever benefit they had when you have to go and hide those dimensions again to explain why we don't see them. So, and by say I mean observe in any way, shape, or form. So the point of this being that people take this and think like, oh, well, science has conquered nature. We now know everything. There are no mysteries left. And it's not true, and it's not true on a very, very relevant level, because it's not just like, oh, we don't know the details. We literally don't know how much basic physics there is that may be going on, using physics again in the sense of territory, not map. Physics properly mostly refers to the map, the study of physical phenomena, not to the physical phenomena themselves. But the sort of the lowermost levels of nature is essentially what's being referred to by physics in the sense I'm using it. And we literally don't know how much of it there is or how much of it we actually know. We have a decent sense of how much of it we're able to observe within physics experiments that we're able to conduct. But physics experiments are a tiny drop in the bucket of observed phenomena. And we have no way of knowing that the things that explain what we can observe in a physics lab are what is the totality of what is going on in all of the observed phenomena that we see. And we have absolutely no reason to suppose that it is. Interestingly, it's mostly atheists who will claim that it definitely is. And the usual retort I've seen is like, well, your Nobel Prize is waiting for you if you can prove one of these other, prove that there's something else. It's like, well, it's kind of amusing actually, because like you would never accept the like, well, it's on you to prove the the alternative. Like, you can't show me how the physics that we have results in the phenomena that we actually observe. I'm just supposed to take it on faith that there would be some way of working this out if anybody was capable of doing the work, which they're not. And that's a pretty ridiculous position to be in, to say that like, I know approximately everything because I know these basic rules. I mean, oddly enough, most of the people just don't even study physics enough to be able to tell you what the rules are. I mean, the sort of books you have to read to actually get into the various equations are really complex, and the math you have to study because you have to do differential geometry, which is a merging of topology with real analysis, essentially, and it's differential. It's incredibly difficult mathematics, and I mean, I only grazed the surface of it, and I knew some people when I was in grad school for math who were working on differential topology, but you basically need differential topology to be able to even properly understand the actual equations of relativity. Most people don't even come anywhere close to it and give themselves credit for knowing this stuff, which is just kind of ironic and kind of gets really to the heart of it, that like, whenever you see this, whenever you see people really pushing it, what they're trying to do is they're trying to take the mystery out of the world, because mystery requires you to be humble. Mystery requires you to admit that you don't know important things. And mystery can be uncomfortable because like the need to act even though there's stuff that you don't know is unsettling. You have to necessarily act in trust. But that is simply the human condition. You act in trust or not at all. And so this is sort of, it's an interesting thing because it doesn't work. The attempt to try to get rid of mystery through saying that we understand physics and physics explains everything it doesn't even begin to work. You have literally no reason to suppose that the physics that we know is the totality of physics. You have no reason to suppose that and you can't, for the phenomena that we actually observe, and I mean things like, an apple growing on a tree. I'm not talking real deep things like humans, even human psychology or whatever. Just like real basic things like a dog walking across the room and munching some food in its food bowl. You have no reason whatever to suppose that the physics that we know could, if you worked it out, actually explain all of this happening. Simply there's no way to work this out. No one's ever worked it out. No one's even come even slightly close to having worked it out. So until such time as somebody tries to work this out and get this as a result, you can't say that that's going to be the result of doing this. There could well be things that you're missing and things that you don't know that are dominating what is going on. And basically, it's when you see this, I think it tends to be it's what you call motivated reason. I mean, some people fall into this by accident, and I think it would be useful for them to be aware of how incredibly limited physics is in terms of our ability to actually measure things, and how you can't actually work out, the phenomena we experience in the world from physics. That the computations are way, way too complex. And by the way, the number of calculations you have to do, that's for like one state change, roughly speaking. So, given that things happen on microsecond by microsecond basis to explain like a full second worth of action, if you have to do 300 years worth of calculations for one glucose molecule for, let's just pretend it's as long as 1 microsecond. Yeah, you're so stupendously far away. You can have computers get, double in their performance for 100 years, and it still won't help. You're still not going to get closer, meaningfully closer to it, because there's just such an incredible amount of calculation that needs to be done for the actual real phenomena. Anyway, so bearing in mind the nature of how you can't do the calculations, and that you can't actually, it's like New Jersey, you can't get there from here. There's a famous song, "You Can't Get There From Here" in New Jersey. If you've ever driven in New Jersey roads, it'll make perfect sense to you. The point is that it's useful to bear this in mind, because there's a tendency in the modern world to equate things like our technological mastery of nature, or more properly, our technological partial mastery of nature. There are lots of things we, can't actually control. But, compared to our ancestors, a few hundred years ago, we master nature to an incredible degree. But to confuse that with actually knowing what's going on, to confuse that with understanding, and to sort of just place off so when you don't know what's going on, but you want to think you do, you have to sort of hide that under some carpet, and the carpet this gets hidden under is physics. Like this is from the metaphor of sweeping your problems under the carpet so you don't see them. And the carpet that this gets swept under frequently is like physics. And I think it's helpful to point out that it can't do the work. That carpet is not sufficiently opaque to hide the fact that you don't actually know what's really going on. So people have that sense, like there isn't anything, there's no mystery left, there's nothing to wonder about, that everything is really known. And it's just not true. It's just so incredibly, ridiculously far from true. And I guess it helps a little bit. I'm a professional programmer, so I'm one of the wizards who makes the magic happen, because people look at something like a cell phone and it's like a little magic brick to them that does amazing magic things. And I've studied how CPUs are designed. I've studied how various components work. I write programs that run on these kind of things. I know how to write the programs to do a large fraction of the kind of stuff that gets done. So it's not mysterious to me, and in that sense. And so I understand its limits. And if you don't understand its limits, you can easily think that we've become all powerful, not in a literal sense, but in sort of an effective kind of sense. And then they're the people going along with our omnipotence as a culture. They're the people who have omniscience too, who know everything. And yeah, I mean, if you actually study it, we can't do everything. There's lots of things that we're at the mercy of nature for. And there is quite a bit that we don't know, and quite a bit that we can't actually know. In theory, not just in practice. So, yeah, it's worth, I think, pointing this out. And I think one of the best things when you come across this, if at all possible, is to get people to actually do the relevant thinking through and the relevant studying. Like I had a friend I was talking about the nature of whether or not a global temperature is raw data or an inference, and I pointed out that it's an inference. It's not raw data, because and I just worked through it just very simply. Like, take this area right here, and pointed to like a field. Now, you want to know what is the temperature of all of the air, because it's not uniform. It's not the same everywhere. So what is the average temperature of all of the air here? I'm like, well, you can take one thermometer, and it's one place, and it'll give you some information. You can take 10, you can take 100, but like, there's a limit to the number of thermometers you can actually place within this. And if you have a fixed budget and you only have 1,000 thermometers, each thermometer is going to be measuring several cubic feet of air at best. If you put them in a grid, and good luck, you're going to need to spend a lot of money on the superstructure to actually suspend these thermometers at all the different points, and it doesn't work to use an IR thermometer over air. So, like, how would you do it? And, well, you've got a finite number of thermometers, a much, much smaller number of thermometers than you have air that you're trying to measure. And so you're then going to average or maybe come up with a model of how it's going to change, how the temperature will be over time. But what you're doing is a collection of calculations and inferring what the average temperature is. And you thought about that, and yeah, that makes sense. And like, now you're doing this for the entire globe, and guess what? You've got a limited budget for thermometers to place over all the air over many miles over the entire globe. And well, I mean, even if you only are taking like surface or surface adjacent temperatures, across, because like the temperature of the ground and the temperature of the air right above the ground isn't the same thing, and which one do you want to count, etc. Anyway, so because like when you've got a rock and it's in the sun and the thing's like 130 degrees, but the air right above it isn't, because it doesn't, there's air is not a great conductor of heat, etc. And so it doesn't change, the temperature is a lot cooler right, a few inches above it or a foot above it, and so on. Which one of these things do you want to consider to be the surface temperature, etc. Yada yada. Anyway, so I pointed this out and just thinking it through, like, okay, suppose you were trying to do it, what would you do? And then thinking it through, like, yeah, you can't. You can't measure the temperature of all the air. There's no way, and to even come vaguely close would require a budget that's absurd and an amount of time that's absurd. So yeah, you can come up with models, and then and a model produces an inference. Like, you're inferring from the data that you put into the model something as the output of the model. So, like, yeah, it's an inference. And when I had him I walked him through, like, thinking it through, like, how would you go about doing this? It made sense to him. He understood it. So I do recommend, if you come across people like this, who really bring to that, just, like, try to walk them through it. Like, well, like, let's look at what would actually be involved in doing this. And then you run up really, really fast against the fact that it's utterly and completely impossible to do. And that tends to get it across to people. Like, if you walk them through what would be involved, and they like actually imaginatively, they do the thought experiment of trying to do it imaginatively, it makes it much, much more real to them, and they can understand it much better. So, yeah, a proper humility to understand our ignorance is a valuable thing. And, in some cases, edge cases probably, but in some cases, this might help. Until next time, may you hit everything you aim at. If you like this video, then clicking the like button, according to YouTube, will make them more likely to recommend it to others. If you know anyone who might get something out of this video, then it would be kind to share it with them, or just share it on social media in general. And if you'd like to see future videos of mine, you can subscribe. And if you're not in the habit of checking your subscriptions page regularly, then I suggest clicking the notification bell and setting that to always, because otherwise subscribing to a channel basically just sort of like gives YouTube a hint that maybe it should consider recommending these videos to you, possibly at some point, if they think so. It's a funny world we live in. God bless.